So, hi everybody, please welcome our next speaker. It is Julie Desjardins, and she will talk about density of rational points on certain Del Pezzo surfaces of degree 1.
Thank you, and bonjour Quebec. I'm happy to speak at this event organized by Université Laval. Today, my talk is going to be very geometric like the previous one. And it's about a joint project with Rosa Winter, who is now a postdoc at Leipzig. So our objects are algebraic surfaces, certain, so Del Pezzo surfaces in particular, and we're going to be very interested in the rational points on these surfaces. So S parenthesis K is going to be the set of rational points. K rational point of the surface that I chose to look. Well, you might be familiar with the density for real numbers, which is the closed sets are chosen with respect to the usual distance. For a Zariski density, though, it's different. So my density in the title is Zariski density. So the closed set are the algebraic subset of the surface. So what are these surfaces that I'm talking about? There's, of course, the Del Pezzo surfaces, so let's start with them. That's a smooth, projective, geometrically integral algebraic surface over K, which is a field, with an ample anti-canonical divisor. So if you don't know these words, it won't matter for you to understand it, since I will be giving you equivalent equation. So if I'm looking in particular to Del Pezzo surfaces of a certain degree, like it was in the title, degree, let's say D, then it's the degree means the self-intersection number of the canonical divisor, like this. So that's the degree. And if the degree is 1, well, that means that we'll have 1 here. Okay, so we'll see an equivalent way with an equation that may speak more to you if you don't know all these words. Another surface that will be very important in this talk are the elliptic surfaces. Our will have base P1, so that's smooth projective, and it's called elliptic surface because it's fibered in elliptic curve. So what does it mean? It means that if you have a fibration into elliptic curve, so you have a fibration from E to P1, such that the fiber of that fibration has genus 1 all the time, except for finitely many values of T. And since you want those fibers to be elliptic curve, you need a section so that you have a point at infinity for almost all your fibers. So, I mean, what will happen is that the finitely many exceptions will be singular as curves. So here are the two surfaces, X, a Del Pezzo surface of degree 1, and E with every ingredient that needs for it to be an elliptic surface. Well, you see, I put a point in red on it. You could wonder, like, if you have an algebraic variety, are there points on them? The elliptic surface has a section, and this implies that there's a lot of point on them. There is the, since I took P1 for a base, there will be the point at infinity for all the curves in the fibration. Now, on the elliptic, so on the del Pezzo surface of degree 1, there is going to be at least one point. Here it is in red. And that point is the base point of the anti-canonical linear system. Okay? And the fun fact about del Pezzo surface, usually degree 1 is considered to be the most difficult. And in my case, I'm using the strategy of blowing up that red point to get an elliptic surface, a rational elliptic surface to be precise. So if I blow up the red point, then I get an elliptic surface. And that's this configuration that I use also, that we use. So I promised you to give you an equation. So this equation is 2 Collard. So what he says is that given so a del Pezzo surface of degree 1 can be given by an equation in a weighted projective space like this. So you put a weight on certain variable by a sextic surface, sextic. So what does it mean? It means that you can represent x like this. So y cube x, no, y square z cube, and then a certain polynomial of degree 4 times x times z, sorry, and then a certain polynomial of degree 6, so that you really have a sextic. So this has degree 6, this has degree 4. For this, the red point, the point that I'm sure I have, is I can give you the coordinate. So this is a x, x, y, w, z. No, that's z, 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 w. And so for an elliptic surface, well, an elliptic surface can be also represented like a family of elliptic curve, and so can also represent it as an elliptic curve with polynomial coefficient, like this. So that's usual elliptic curve, although there's these coefficient. And if it's rational, then f will have degree 4 and g will have degree, less or equal to 4, and g will have degree less or equal to 6. So you can see now that there's indeed the link between them. So what is the result I would like to talk to you about? It's this theorem. So we are looking at that surface, and you'll see next why it's interesting. So if that surface contains a rational point that is non-torsion on its fiber, then the set of rational points is Zariski dense. So we are on a field of characteristic 0. And if we're on a number field, then the converse is true as well. So what about the field of characteristic 0? I must say that originally we started proving it for number field. And then so during a correspondence with Koyutelen, he gave us an argument to generalize this to general field of the characteristic 0. So that's a good improvement, right? So thank you. Okay. So let's see why this is interesting. So this is, Manin started looking at that question of whether, so if you have a rational elliptic surface, is the set of rational points Zariski dense? Because we know that there are points, and now what about, and we know that there's many of them, are they dense for Zariski topology? And the answer is yes for a lot of these surfaces, actually almost all, except well, the one that we're considering. So not exactly, but you see how close it is. So here are what is known for Del Pezzo surface. So the minimal model of a rational elliptic surface can either be a Del Pezzo surface or a conic bundle. And so when the Del Pezzo surface has degree 3 or more, or is a conic bundle, it is proven that the Zariski density of the rational point. There is a finite exception to DP2, and DP1, the results are partial, and I won't give you an overview of all the results that there is, just because I'm lacking time, sorry, to the people I'm not citing. Although I'm going to speak to you about another strategy, which is arithmetic. So the root number, which is equal to the parity of the analytic rank. So under BSD conjecture, or just a weak version, you only need a weak version of it, BSD. And also I need to say, okay, let's be careful here. Let's just say there is, so the functional equation makes sense, so that we can speak about it without fear, okay? So it's under BSD equal, the root number is equal to the parity of the geometric rank. So the rank will be non-zero if and only if there is infinitely many, the rank would be non-zero if the root number is -1. But not if and only if. So if the root number is -1, then under BSD, the rank should be even and so non-zero, odd and so non-zero. Sorry. So if E is non-isotrivial, so meaning that it's not a family of twists, then it was a result in my PhD thesis to prove that the root number varies. And this shows also the density, of course, under this conjecture, and also under another conjecture that I'm not speaking about today. If E is a family of twists, so isotrivial, I proved with other mean, not with the root number, that the points are Zariski dense. And if the J invariant is 0, Verily Alvarado proved in his PhD thesis that if it's not of that form that I've written, then it's not, it might not be dense, although in some cases it is. So what you need to be aware of is that in particular, it's not proven for the surfaces that we're interested in. These surfaces also have the property that there's some points that are the intersection of many lines on the Del Pezzo, and this is also for the partial result on DP1 that I've not spoken of, is also an exception. So what we're using almost all the time, I mean, I was also using this in my PhD thesis to prove the density, is this important fact. So you have Zariski density if and only if, I need to say if K is a number field, otherwise you only have one direction like this. So I don't know how to say this. So number field. If it's a number field, it works. So if and only if you can find infinitely many fiber with non-zero rank. The idea is that if there is many, so if your fiber has non-zero rank, then there's a lot of points on it. And if you have lots of fibers with a lot of points on it, then Zariski density holds. Okay, so our strategy is to use this, and what we're going to do is to construct a multi-section with a lot of points. So if a section is a curve meeting all the fiber once, then the multi-section meets all the fiber a certain fixed number of times. And in our case, that's going to be 3. Okay, here's a sketch, very sketchy of the proof. So it's not very detailed. Each step is actually hiding a lot of details. So if you remember my theorem, I started with a point non-torsion on its fiber. So here it is. So that's P. And so the first step to the proof is to construct a 3-section passing twice through P, which means that we'll be in a situation like this. So we're constructing it on the elliptic surface associated to the Del Pezzo. Okay? And now that we have this, this 3-section, we need also to prove that the normalization, you see it's singular. So we need to study the normalization. It's an elliptic curve. And that elliptic curve has positive rank. So meaning that there's a lot of points. Sorry, there's a lot of points on my section. But now those points might not be, so the point of the surface can be all concentrated around this curve. And we need to prove the 3rd step to show that it's not. So if you take one point of C, you need to show that on its fiber, let's say I'm taking this one, and then I'm taking this fiber on which it lies. We need to prove that that point, okay, this one, is non-torsion. So that's those 3 steps that contains a lot of details. Since I have maybe 30 seconds left, I'm going to speak to you about a bit more about the second one. So the way we prove that it's first an elliptic curve and then lots of points is with this automorphism. With it, we can notice that there are 2 more singularity, and those singularity correspond to this automorphism applied to Q, and then the automorphism, that's the automorphism of C. And then you have these 2 points, that the two singularity of the curve. And then you can also use those 2 points to find another point, which is, if I remember correctly, the sum of them. And this is the point that will show have non-torsion. So my time is up, so I thank you for your attention.
Thank you.